Welcome to this lecture where we're going to talk about queues. We'll do an overview of the main aspects of a queue, and then we'll talk about implementing a queue with linked lists or arrays as the back end, and what those implementations might mean in terms of how they affect the performance, the analysis of the queue's methods. So of course, a queue is, as you probably know, a first in, first out data structure, which allows us to add to the back and access only the front and remove from the front. And this is used for first come, first served ordering, such as people standing in a line to be served or to buy something. You might think about buffering data between a producer of data and a consumer of data, like if you have a computer connected to the network might be sending a lot of information to your computer. Your computer might not be ready to process all that information as soon as it arrives. So the connection to the network, your network card or your Wi-Fi chip, might be buffering some of that data and accumulating it at the back of a queue and removing it from the front of the queue as it arrives and as your computer is able to process it. And a queue can also be used to implement, as we've seen, the breadth first search algorithm. And in this case, the queue is serving to process the things that we discover in the order at which we discover them. And this is useful because it allows us to find shortest paths in a maze, for example, by looking at all those things that are closest to where we start and then one step away from where we start and so on. So the main methods that we need to implement for a queue are the ability to get the front, see what's at the front, to enqueue or add something, to dequeue or remove something, and to tell if the queue is empty. And of course, we enqueue at the back and we dequeue at the front. So I want to do some analysis for this if we were to implement a queue as a linked list. Okay. The data members that we'll need to do this well are a pointer, which is the front, and a pointer, which is the back for the queue. And then for each node, we'll have a data field or a data member and a next pointer, which points to the subsequent node in the linked list. Now, let's look at these methods one by one. It's easy to tell if a queue is empty by checking if the front or the back or both are null. And it doesn't matter how long the queue is, because all we have to do is look at the front or look at the back. If those are null, then the queue is empty. And if they're not null, then it's not empty. So we can check that regardless of how long the linked list is in constant time. All right, so it doesn't matter if there are 100 items in the queue or 1,000,000 items in the queue. We can do this in the same amount of time, constant time. Also, similarly, getting the front of a queue is very easy. We just dereference the front pointer to get this node and its data, and that gives us what's at the front of the queue. And all we have to do is follow that one pointer, assuming the queue is not empty. You wouldn't ask a queue for its front if you knew that it was empty. So you should always check if it's empty first. But all we have to do is dereference that one pointer, which doesn't matter how long this linked list is. We have only to do that one thing. So that's constant time. Now let's talk about enqueuing and dequeuing. If we want to enqueue, we enqueue at the back. So what we need to do is a few steps. We have to allocate a new node, say on the runtime heap. We're going to make what back's pointing to, its next, should no longer be null, but make it point to this new node. And let's suppose that this new node, we have a local pointer called t, which points to it. Okay, so we've created this new node on the heap. We've made back's next point to that node, and then we change back to point to that new node. And those are essentially the 3 steps we need to do, as well as fill in whatever data belongs in that new node. So those 3 or 4 steps are all that we need to do. And it doesn't matter how long the queue is, how many elements are on it. It's going to take us only those few steps. So that's order 1 time. And again, the order 1 here just is saying if the queue had 0 elements or 10 elements or 1,000,000 elements, it still takes the same number of steps. So that's why it's order 1. If we want to dequeue, we dequeue from the front. And the way we would do that is we would make a pointer, a local variable which points to the current front so that we can delete it later. Then we'll make front point to what front arrow next was pointing to, right? And then we'll null out this pointer right here. We'll make that equal to null. Why would we do that? Well, in case deleting this node right here has a cascading effect, if the destructor for this node were to call delete on the next node, then we don't want the rest of this list to disappear. So we would null out this pointer, and once we do that, then we can delete T, and this node goes away. And so those few steps, 3 or 4 steps, are all that we need to do in order to dequeue, regardless of how many elements are on the queue afterwards. So that's also order 1. So the nice thing about a queue is that we can implement all these 4 important methods in constant time. Now I would like to do a real quick thought experiment. Could we swap the pointers front and back? So could we make this the back and this the front? And let's think about how we could do that. Let me first pause this and erase what I've done here. Okay, so could we swap the back and the front pointers? So what if we called this back? And what if we called this front? Well, could we still get the front easily? Yes, because we still have a pointer directly to it. Could we tell if it's empty easily? Yes, we could just check if either of those pointers are null. Could we still enqueue in constant time? Well, we would enqueue to the back, so we would create this node, make it point here, right? Make the back point here, and we'd be done. So that could be done with a fixed number of steps, and that would still cost order 1. But the cost of dequeuing actually is what changes here. If we called this the back and this the front, we would want to dequeue from the front, meaning that we would want to get rid of this node and make this pointer for the front point not here, but to here, right? But the only way we can't follow this node link backwards, that's impossible. We would have to go all the way to the back and walk all the way towards the front again, stopping at the one just previous to what the front was, and that would cost us order n. And of course, that would be terrible from a runtime perspective. So we don't want to do that. But it's just a nice thought experiment to see, would that work? Well, yes, we could make it work, but it would be much slower. So it does matter which of these ends of the linked list is the front and which is the back. Let's now look at an array backing for a queue. And again, we have the same 4 methods because this is the same data structure. It's just a queue. But we have a different representation. We have the array, we have the capacity for the array, which in this case is equal to 10 because we have 10 elements. We have the front, which we'll say is where we would grab the front of the queue, which is currently 0. Okay, the front is right there. And we have the length, which of course starts out as 0. And whenever we want to notice we don't have a data member for the back. We could implement the back as back equals the front plus the length. And of course, since the queue is empty right now, that means the back is also at 0. That's the place where we would actually put something as the next added entry in the queue. The next enqueue would go at back, at front plus length. Okay, so if we wanted to enqueue, well, let's talk about the simple things first. Can we tell if it's empty? Yes, it's empty if the length is 0, and we can check that in constant time, no matter how many things are on the queue. Can we get the front element, assuming that it's not empty, right? Well, the front element is just where the array subfront lives. So we just look that up in the array, which we can do in constant time, and we return that value. Again, assuming it's not empty, because if it's empty, that is not a well-defined thing to ask a queue. You can't ask an empty container, what's your first element, right? That doesn't make sense. Now, if we wanted to actually enqueue something, let's enqueue a few things. Suppose we enqueued the letters A, B, C, D. So I would enqueue where? At front plus length, because that's the back. So if I wanted to enqueue the letter A, it would go at front plus length, which is 0. And then length, of course, would change from 0 to 1. Right, so now the back is here because front plus length is now 1. And if I wanted to enqueue B, then the length would change to 2, C, D, okay? And the length would change to 4. The back now is sitting right here, right? Right, the back is 1 past where the last valid element. So you'll notice that each of those steps all we had to do was assign into the array. Well, first we had to compute where the back was. That's one operation. We had to assign to that position in the array. That's another operation. We had to increment the length. That's another operation. And since it's basically three operations, enqueuing into an array that has enough capacity is just order one time, which is nice. If we want to dequeue, well, we would dequeue from the front, which currently is 0. And what we could do, this is not a good idea, is we could sort of remove this element and then move everything to the left so that the front is still 0. But doing so, of course, would cost us a lot, because if this queue was really long, we'd have to move a lot of data over just one element, one index, just because we created a hole there. But if we pretend like it's okay to have a hole there, in fact, it is, because we have this data member front, which allows us to position the front anywhere in the array. So if instead of doing it that way where we shift the data, what we could do is we could just make the front be 1, increment the front, and of course, we would need to decrement the length from 4 down to 3. And then when we do that, the front now becomes pointing here, right? So where did A go? It didn't go anywhere. It's just no longer, logically speaking, it's no longer on the queue. It's in the array, but it's no longer in the queue. The queue starts at index 1 and it ends at index 3, and 4 is still the back. Notice that the back is still at the same position because we incremented the front and we decremented the length. So dequeuing costs us order one time because all we had to do was increment the front and decrement the length. And we didn't even have to do anything with this thing right here. We just let it sit there, okay? So we can do all of these things for an array-based queue in constant time. And notice that's the same as what we had for a linked list-based queue, okay? There is one more important point to make, though, for an array-based queue, and that is the issue of circularity of this array. So suppose we added a whole bunch of things to our queue. So suppose we added E, F, G, H, I, J, okay? And we've run out of room over here. There's no more space. We have no more capacity. But notice this element right here is not being used, and that's actually where we could put the back, right? We could reuse this slot right here because it's not currently being used. And if I were to sort of be careful about this, I would say the capacity is still 10, the front is still 1, the length is now 9, right? So we're not full. The queue is not full because we still have one more empty spot, and that empty spot is right there. But we can't use it unless we use a circular representation. So I'm going to skip to the next slide. All this writing is going to go away, but let me sort of advance our example. Suppose instead we had, the front was here, so the front was 6. Let's suppose the length was, 5, okay? So then I have A, B, C, D, and then E. And the capacity is still 10. How would we indicate that the back is here? How do we indicate that we want to circularly move around the array? And if you haven't seen a circular array, let me introduce that idea real briefly. I assume you've probably seen this before, but the idea is you can go past the end of the array by wrapping back around to the beginning of the array at index 0. And you only go that way. You don't go backwards. You don't go this way, right? You only go off the end of the array this way and circle back around to index 0, okay? And for this, the modulus operator becomes essential. It's really the best way to do this. In order to calculate the back now, we don't calculate front plus length. We calculate front plus length modulus the capacity. So this is the key right here. So 6 plus 5 is 11. 11 modulo 10, which is our capacity, is 1, and that tells us that the back really should be right here, okay? So a circular array allows us to reuse this portion of the array that is currently not being used, even though the queue logically starts here and logically ends here, right? Everything else works just as we intended. I mean, we can tell if it's empty because the length would still be 0. We can get the front because we just index where the front is pointing us to. And we still know where the back is. We can calculate it like this. We just wrap around when necessary. One other thing that you have to be careful of, though, is suppose that you dequeued a bunch of items. So you dequeue A, then you dequeue B, C, D. Then front also needs to wrap around to the beginning. So every time you uh, increment front, you want to increment front modulus capacity. So front equals front plus 1 modulus capacity. So if front was here and we add 1, front would be 10 modulus 10 would bring us back to 0. Okay? One warning that I will give you is that whenever you use modulus, it can be tempting to sometimes subtract and then take a modulus. Don't ever use subtraction when using modulus because the modulus operator, at least in C++, and this is different for different languages, but in C++, if you take a modulus with a negative number, you oftentimes will get a negative number. And that's usually not what you want. And that's why I say we go off the array, the end of the array this way, and we compute the modulus. But we don't subtract and go off the end of the array this way, because if you took -1 modulus 10, you'd probably get -1, okay? Instead of 9, which you might think you would get. All right, so again, all of this, we can still do constant time for all of these operations. Nothing really has changed here. We've just added the ability to wrap around the end of the array. So here is a summary of what we've looked at so far for linked lists and stacks and queues. And this is again for linked lists, arrays, and linked lists and arrays. And what I want to point out to you is that basically everything except what I'm circling, everything except for these three is constant time, meaning that if you implement a stack with a linked list or with an array, if you implement a queue with a linked list or with an array, you're going to get constant time behavior no matter what. And only with a list do you get these differing behaviors depending on how you use the list, as we've already talked about. So does the implementation matter? Well, for the list, yes, depending on how we use it. For the stack and the queue, not theoretically, but there are practical considerations, such as the memory usage. With a linked list, right, you're using extra memory for each pointer, whereas for an array, you don't have all those additional pointers. Also, arrays tend to be faster because they are contiguous chunks of memory, and computers do much better at accessing one element after another due to what's called spatial locality, which means you can, if you go to this point in memory, you're likely to go to this point in memory right after it, and so the computer optimizes for that fact. However, if you don't have large chunks of contiguous memory, then a linked list might be your best bet. Or if you only want to allocate exactly as much memory as you need, then a linked list might be your best bet here. And again, theoretically equal, so order 1 versus order 1, does not mean that they are practically going to behave exactly the same way. So it depends on the compiler, it depends on how you've programmed it, etc. But at a high level, you can use a stack, or you can use an array, or you can use a linked list to implement a stack or a queue, and asymptotically speaking, you get the same runtime performance, which is good, and it's a good thing to keep in mind and to know.